Welcome to Study Loop.
41.34, there are these two things we're supposed to show that are true. This has to do with if we have an undoped semiconductor, we can have a simplified model where we replace the actual distribution of energy states with just having NV states in the valence band that all have the same energy, and NC states in the conduction band that all have the same energy. And given that, and if the number of conduction electrons is equal to the number of valence holes, we need to show that this is true. And then the next part, if we have going from this, if the Fermi energy is in the gap and the difference between the Fermi energy and the conduction and valence energies is much larger than the thermal energy, we can derive this expression. So the number of electrons in the valence band is this NV, so the density of valence states times the occupation probability. Right. Okay. So EV minus EF over KT plus 1. Now in the valence band, we want the holes. So the number of holes in the valence band, since the number of available states has to add up to the number of available states, we can subtract this expression we just found from NV. And we'll end up with this. And this is one of the things that is supposed to be equal to the other. This is delta EV. So far things are looking good. Now the number of electrons in the conduction band is again equal to the density of states times the occupation probability. The exponential of the difference for the conduction band, for the thermal energy, plus 1. So since these two things are supposed to be equal to each other, then these two things are equal, and that's what we were asked to show. Now for part B here, we're saying that the energy difference between the conduction and valence energies and the Fermi energy are large, and the Fermi energy is in the gap between the two. And so the exponentials are going to be much greater than 1, which lets us write slightly simplified form. Where we've left out the plus 1s in the denominators because they're negligible compared to the gigantic value of the exponentials. So recall that this is EC minus the Fermi energy, and this is the Fermi energy minus EV. So we can rearrange this. Over KT is equal to the ratio of our numbers of states. So we take the logarithm of both sides, and that gives us our log of NV over NC. We have this the difference here that becomes the sum of these two, and that also goes over here, and then we divide by 2. And just like we were supposed to, we find that the Fermi energy is 1/2 times the conductance and valence energies plus this KT log NV over NC. So now we want to show that the Fermi energy is near the center of the gap when NV and NC are roughly equal. And we can see here that they're going to go, this ratio is going to be 1. The logarithm of 1 is 0. And so we're just left with the average value of the two energies, which will be directly in between, or directly in the middle of the gap between them.